when we talk about this stuff called conditional probability is going to lead us to the main point in probability, which for us is independence. So we want to look at things and see if they're independent, and we can do that through this thing that we call the conditional probability. All right. And when we talk about the conditional probability, a conditional probability says that if an event occurs already, given that you have some information about an event, what's the probability of another event occurring? And what that really means is you can think of it simply put, if you're in if we're on, does anybody have their camera on right now? For instance, here's what I want to know. The probability that you wear glasses, right? The probability that a person wears glasses, given that they have their camera on right now. Well, in order for this to work, what I would do is I would look at all individuals. We started with everybody in the class, right? If I ask for the probability that a person wears glasses, given that they have their camera on, what piece of information do I have to even be included in that sample? Can anybody answer that for me? Probability that you wear glasses, given you have your camera turned on. Who's included in that sample right now? Anybody? Anybody?
14.
Well, I'm just saying in general, who will we include? Don't even try to give me a number. I don't really care about the number. Who do we include in that sample, right?
Just the
Well, we're going to include,
on.
thank you, just the people that have their cameras on. So what we're doing in a condition is we're restricting the sample size. If we think about it like this, we start off by saying everybody's included in the sample right now. When we add a given though, in order to actually fit into the sample, you have to meet that condition first. Once that condition is met, then we look at you having the other condition that's being asked for. And so this is read as the probability of A given B. Read as the probability of A given B. And here's the symbolic notation of it. It's A, the vertical bar means given. So this bar right here just means given. And what this is basically saying, given that B has occurred, given that B has occurred, now I want to know what is the probability of A occurring. And so the way this works is, because we're looking at this right here is going to be our restriction. That's what we're restricting the sample size to. We call that the restriction here. We're placing a restriction which says you have to be in B first. And then once you're in B, this up here, remember, is the intersection. It's the intersection of A and B. So this is our intersection of the two events. It's the intersection of A and B. That's what we're looking at. So when we start to explore this particular thing called conditional probability, right? We're going to first look at the back letter. That's what I want you to get in the habit of, looking at the back letter. The back letter is going to be your restriction. It's going to be the bottom. It's going to be what you're restricting the sample to, right? Once you have it restricted, you're going to look at the letters together and find their intersection. That's going to be the people that are actually included from the restriction. So here's an example. Same one we've been talking about. And we're going to look at this from a couple viewpoints. We've looked at things through tables so far. We're going to look at things through, we're going to build trees now too, all right, a decision tree. And so Electronics World, same survey, people bought either a refresh rate TV, the refresh rate was either faster or standard, right? Either they bought remember those are mutually exclusive, they can't occur at the same time, or either they bought a streaming media player with that TV. It was either yes or no. So in a decision tree, here's what happens. We're going to put the first mutually exclusive event on the outside, all right? And we start off by saying, in this particular case, remember we used the complement notation where we said faster was, it's called faster F, and standard FC. So in this particular thing then, if we look at it, here's what can happen in your first decision that you're gonna make. Either you purchase a faster refresh rate or you purchase a standard refresh rate. So here is F, you purchase a faster refresh rate, or here is FC. You did not purchase a faster refresh rate, which means you purchased standard, right? And when I look at this, then how many people purchased a faster refresh rate TV? Can anybody tell me that?
80.
80. 80 out of how many total?
300.
Thank you. So in this first box, we're just going to write 80 out of 300. And actually, I don't like writing it. I actually like writing the decimals because I do more with those because we're going to do most multiplication. So I'm just going to do 80 divided by 300 and give you the decimal, which is 0.267. But in case you don't know how I got that, I did 80 divided by 300. Why did I do 80 divided by 300? How many people purchase a faster refresh rate TV? 80 people, right? So how many people didn't purchase a faster refresh rate TV? Well, we can do what to get that? We can look at these people that purchase standard rate. That's how many people? Y'all talk to me tonight. 220. Y'all talk to me now. Y'all keep me up tonight. Let's go. So y'all talk to me. Y'all can come off mute and talk. So we have 220 out of 300. What's that going to be equal to? Well, remember, these are mutually exclusive events. And in particular, they're what we call collectively exhaustive. Collectively exhaustive means that you have to fit into one of the events to be in the sample. So if this percentage of people fit into this event, and this is everybody in the sample, then we can just subtract this from 100, and we should get 0.733. I think that's what it was last time too, by the way.
Yes.
All right, cool. Thank you. Now, the next part says this then. If you read this tree, we're looking at these people all purchased a faster refresh rate TV. These people, we call the streamers, we call those S. Call those S. So here's S, here's not S. Yes and no. Streaming versus non-streaming. So this is, if they purchase a faster refresh rate TV, they could also purchase a streamer with it, a streaming media player. Or they could not purchase one here. Likewise, if they did not purchase a faster refresh rate, they purchase standard rate, they could purchase a media player with it, S, or they could not purchase one here. So when we read this now and then, when I read this, I'm going to read it as what percentage of people purchase a faster refresh rate TV and a streaming media player? That goes right here. Everybody understand that?
Yes.
These are the faster refresh rate TVs and the streaming media player. What percentage of people did that? How many people did it, by the way? Let's start there. How many people did it?
38.
38 out of how many total?
300.
300. So I'm going to go 38 divided by. So in this box, I'm going to put in 0.127. Right? Bigger. 0.127. And in the next box, I'm going to look at how many people purchase a standard refresh rate TV, right? That was a faster standard refresh rate TV. Well, that's what percentage again? Somebody, what's that equal to? That's 42 out of
It's
300. Thank you so much. So that's 0.14. So 0.14. Now, if I add these two values up, 0.14 plus 0.127, look what they equal. They equal that first branch on the outside. Does that make sense?
Yes.
Does everybody understand that? That makes sense. They equal that first branch on the outside. They equal the mutually exclusive events. If I do the exact same thing for the other one, for the nose, I had 70 people get a standard rate TV or FC and a streaming media player. So that's 70 divided by 300. And I get 0.233. So this box right here is 0.233. And the other one was 150 right? 150 divided by 300, because we had 150 people in the other box, 150 people over here out of 300 not get a standard refresh rate or a media player. So this is I'm sorry, 150 divided by 300 is just 1/2 or 0.5. And again, if you add those two values up, 0.500 plus 0.233, look what I get. I get this first branch sitting out here. Now, likewise, I can also do some other things with this. I can look at the percentage of people who purchase a streaming media player as well. And the sample, that's what percentage? What percentage of people purchase a streaming media player? Can you tell me that? That would be what numbers? Tell me the actual fraction. Streaming media player, how many people is that?
108.
108, thank you. 108 divided by 300. I get 36%. If I add up the streaming media player branches, by the way, 0.127 plus 0.233, that would be this branch purchase stream media player, this branch purchase stream media player. That's equal to 0.36 as well. So the tree itself, if you do the other one, by the way, you're going to get 0.64, probably 0.64. So the tree itself is just an extension of the table, by the way. The tree itself is an extension of the table. I want you to understand that first off. So all I'm doing, I'm showing the table in a different format, and it's called a decision tree. Now, does it matter what format you use? Not really, it's preference. It'll be preference, and eventually for some of you. Some of you are going to prefer one or the other. Some of you are going to like, I can't do this one, I can only do that one. That's fine. But sometimes it makes more sense to use a tree than it does a table. Sometimes it makes more sense to use a table than it does a tree. But the way this works is that when we do this, we can go from a tree to a table. Yeah, I think I let them in. I hope I did. Thank you for letting me know that, by the way. Let me go back over here so when y'all go back and look at this, you know what you're looking at. Let me put the actual numbers over. This was 80. This was 80 over 300, right? This was 220 over 300. Put those in there so you know what we actually did right there. This one was 38 over 300. This one was 42 over 300. This was 70 over 300. This was 150 over 300. Right? You okay with that?
Yeah.
All right. So I'm just putting those numbers on saying when you go back and look at this, you know what I actually did. Let's go to the next part then. Looks like I did all that work right here too, by the way. So you can see it there. So here's why I'm doing that now. What we're going to do is we're going to develop this concept we call independence. This concept we call independence. So an independence says if events A and B are independent, then the probability of event A occurring has no effect on the probability of event B occurring, right? So if two events don't affect each other, they're what we call independent. Let me ask you a question. Does that mean those two events are mutually exclusive? Yes or no? What does mutually exclusive mean again? Anybody? What's mutually exclusive
You
mean?
can't have one without the other.
Close. Keep going. That's more collectively exhaustive. Mutually exclusive, what does that mean?
They both occur?
Not quite. Mutually exclusive.
One or
If
the
you're
other?
exclusive, yes. If event A occurs, event B cannot occur. Mutually exclusive says if event A occurs, event B cannot occur. Is that the same thing as independence? Is that the same thing as what independent means? Two independent events. This says if event A occurring has no effect on the probability of event B occurring. So are those the same concepts, yes or no?
No.
Are those same
Yes.
concepts? Try it again.
No.
Think
No.
about this.
No.
The first one says that event A occurs, event B cannot occur. You are a smoker. You cannot be a non-smoker. That's what mutually exclusive events are. You are a drinker. You cannot be a non-drinker. Mutually exclusive. You bought the faster refresh rate. You cannot buy the standard refresh rate. Mutually exclusive. Independent says that you're a smoker and you can also be a drinker. But you being a smoker has no effect on you also being a drinker. They're two independent events. Those events aren't probably independent, but that's what we're trying to establish here. If this event occurs, it has no effect on another event occurring. For instance, if I watch a game tonight, it has no effect on you going to sleep tonight. That's two independent events. All right. So that's what we're saying then when we say that, when we talk about independence. All right. If one event occurs, the other one cannot occur. I mean, that's mutually exclusive. If one event occurs, it has no effect on the other event occurring. And here's what we do. We assume a lot of things are independent. This right here is an assumption. This is what we call the assumption of independence. And it's called the multiplication rule. And what it says is this: the probability of two events occurring in sequence. So the probability that I do something and you do something, the probability that I do something and you do something is equal to just the probability of both those events multiplied by each other. So the probability that I speed on the road may be 75%. The probability that you speed on the road may be 50%. The probability that both of us speed when we're on the road is 75% times 50%. That's what this is saying. If two things are truly independent. And so here's what this says. Because of that, we can actually develop what we call the mathematical definition of independence. So this is an assumption. We always start off with the assumption. But if that assumption is true, then the mathematical definition says this. This is the mathematical definition of independence. And what it says is the probability of A given B. Well, the probability of A given B, this right here, remember what that's equal to? What is the probability of A given B equal to? What do we start out first? We restrict with what part is restricting, A or B? What part does the restricting, A or B?
B.
B. So we restrict with B first. So this says basically then you restrict you look at the probability of B, and the top is going to be what though? Remember we said the top was going to be? The top was the probability of A and B, or A intersect B. This right here, by the way, this right here is the same thing as the probability of A and B. Intersect B, that means and. So they're the same things. We can recall them that A and B. Now, if two things are independent though, this right here, A and B, or this right here, A and B, is equal to just the probability of A times the probability of B. So this is actually equal to the probability of A times the probability of B. All of that is divided by the probability of B. Does everybody understand what I just did there? All I did was I started off with, this is what conditional probability says. We restrict to the sample first, and then we look at the intersection of the two events, A and B. But if we assume that A and B are independent, then we can just multiply this and part as A times B. So A times B, right? But what do you notice is on top and bottom of this equation? Both the probability, good, they both have probability B, so we can cancel those out. And this tells me then that the probability of A given B, if two things are independent, is equal to the probability of just A. This is the definition of independence. This is the definition of independence. If two events are truly independent, then what this really says is that given that an event has already occurred, it should have no effect on another event occurring. Because remember, this is a conditional probability right here. This is conditional. So this is given something has already occurred. So given that B has already occurred, this is saying that it should have no effect on A occurring because A is going to be equal to whatever that marginal is. And so I'm going to show you what this means when we look at this table right here, right? And again, we have the same thing. So we have the here's how we do this. So we're using this table again to determine whether it's being satisfied with the purchase. Oh, this is actually different, huh? Yeah, this is different. Glad I read that. So this is talking about the following survey represents 300 households that actually purchased large TVs. The households were asked if they were satisfied with their purchases. Determine whether being satisfied with the purchase and the refresh rate of the television purchase are independent. So we have two events. Let's go ahead and label our table first as faster refresh rate F, standard refresh rate FC, not fast. Let's go ahead and label the yes as, we'll call that satisfied with the purchase. We'll call that S again. That means you're satisfied. Not satisfied with the purchase, SC. Okay with that?
Yes,
All I'm
sir.
doing is labeling table with the notation. Good. So I want to determine whether being satisfied with the purchase. Determine whether being satisfied with the purchase and the refresh rate are independent of each other. Are independent of each other. Right? And so the way this works is like this. We're going to show, we need to show this. Remember the definition says that the probability, we need to create what we call a conditional first. So here are the steps, by the way. Here's what your steps are. First step, you're going to find a conditional. There are two conditionals you can actually find here, but they have to involve what two events? What two events am I looking at here? Can anybody tell me the two events I'm looking at? What are the two events I'm looking at?
Satisfied with the purchase and the refresh rate.
Refresh rate. Good. So I'm looking at F and S. I'm looking at F and S. I can find two conditionals based on that. I can find the probability of F given S, or I can find the probability of S given F. It doesn't matter which one you find. It doesn't matter which one you find. As long as you set the formula up correctly. And what do I mean by that? If you are finding F given S, if you are finding F given S, in order for the two events to be independent, this has to be equal to the probability of the first event, F. If you are finding S given F, this has to be equal to the probability of the first event, S. And so what we do first is, let's find the probability of F given S. F given S. Well, again, when I start this, F given S, who am I restricting to? Who is going to restrict, who am I restricting to here? F or S?
S.
S. So look at how many people sit in the yes category. How many
60,
people are in your S's?
240.
40.
So my bottom of this fraction is now 240. I'm looking at only these 240 people that said yes. Out of those 240 people, who am I interested in now? The ones that said yes, and they had a what?
Faster with 64.
And they had a faster refresh rate. So that's 64 people. That is the conditional probability of F given S. That is the conditional probability of F given S. We okay with that? Go find the conditional probability of S given F. I'll give you a few minutes to do that. Go find that conditional probability of S given F, please. All right, so for this one, when we look at this particular one, now we're going to restrict to, what are we going to restrict this one to? S given F. What do we restrict here?
80.
The 80 people that purchased the faster refresh rate. So we'll put 80 there. And out of those 80 people, who are we interested in? The same 64 that purchased the faster and refresh rate. So look, the tops of these will not change. The top should be the exact same. The bottoms are going to change here. But if the two events are truly independent, here's what they should equal then. The second step, once you find a conditional, your second step, you find the marginal. So you find the margin of the first event. In this particular case, this first one needs to be equal to the probability of F. What is the probability of F? Can anybody tell me that? What is the probability of purchasing a faster refresh rate TV?
40 out of 64 out of 240.
Try that again. That's faster, and yes, I only care about I really only care about faster. How many people purchase a faster refresh rate TV?
Oh, 80.
80 out of how many total? 300. 80 out of 300. Now we go back to the entire sample, because what this is saying is this: the fact that you purchase a faster refresh rate TV has no effect. If the two events are truly independent, the fact that you purchase a faster refresh rate TV, which is all these people right here, has no effect on you purchasing or on you being satisfied. If those two events are independent, then these probabilities should be exactly the same, because this probability should have no effect on this probability right here. If they're not equal, though, what that tells me is that they do have an effect, and it is dependent upon your satisfaction is dependent upon your refresh rate. So if I calculate those, 64 divided by 240, make it a decimal. This is 0.267. I want to know, does that equal 80 divided by 300? This is also 0.267. Because they are equal, then we can say yes, they are independent. Because they are equal, we can say yes, they are independent. If they are different numbers, if there are different values down there, then they are not independent. But because they're the exact same numbers, they are independent. Now, here's why I want to show you can do either or. If it is independent here, it will also be independent here when I do this. And to calculate that, when we do 64 out of 80, right? That needs to equal what over here? Well, here it equals the probability of F because F was in the front. Here it equals the probability of S because S in the front. What's the probability
40.
of S? 240 out of what?
300.
Thank you. So that's 240 out of 300. Are these two values equal to each other? 64 divided by 80, 0.8. 240 divided by 300, 0.8. They both equal 0.8. So what does that tell me? They are independent of each other. If two things are truly independent, then it doesn't matter what condition you check with. As long as you set this formula up correctly, if they are truly independent, these numbers will always be equal to each other in the end. This is how we show that things are independent mathematically. We can assume that your refresh rate and the satisfied purchase are independent. We can assume that. We use that assumption-based independence. But this mathematically proves that they are independent. This tells me that your refresh rate has no effect on your satisfaction. So let's try another example. It says that, do millennials or Gen Xers feel more tense or stressed out at work? The survey below was conducted online. Use the information to answer the question. So you have the age group, you have your millennials and your Gen Xers, then you have your stressed out level, yes or no. So let's go with age group, let's go age group, we'll call that A. So I'll call millennials A, I'll call Gen Xers not A. They feel tense or stressed out at work. So tense or stressed out at work, I'll go T. Tense is T. TC is not. Let's try to answer this first question. And it says, given that the employed adult feel tense or stressed out at work, what is the probability that the employed adult was a millennial? What am I asking you to do here? Am I asking you to show independence yet? Yes or no? Have I asked you to show independence yet? Yes or no?
No.
No.
No. But the key word here is this first word that says given. This word means I'm going to do a conditional probability. And given that the employed adult felt tense or stressed out at work. So who do I care about right now? Do I care about everybody in the sample?
No.
I only care about who?
The people who are
Millennials.
The people who did what? Not the millennials just yet. Who do I care about? The people who
felt tense. The people
tense
who
or
were
stressed
talking.
out at work. I only care about these people right here, the ones that felt tense or stressed out at work. These are all the people I care about. So look, when I write this, then I know that I'm restricting the sample to the tense people. I'm restricting the sample to the tense people. Out of those tense people, which ones am I actually interested in though?
Millennials. So A.
The millennials. So I'm interested in A. Good. I'm interested in A. And when I set this up, I know the bottom of the fraction needs to be T, right? How many people are in T? How many people are in T?
358.
358. So out of these 358, who am I actually interested in?
The millennials. So
These
175.
these 175 millennials. It's 175 out of 358. And I'm going to write that as a decimal, which is 0.489. Given that the employed adult is a millennial, what is the probability that the person felt tense or stressed out at work? How is this different? How is this problem different?
The restriction
Keyword.
is the millennial.
Good. You're changing your restriction. The keyword is a given again. So given that they're millennials, so the probability of given that they're millennials, so your back is going to be your restriction. I'm restricting it to the millennials, A, right? Out of those millennials, who am I interested in now? The ones that felt tense or stressed out at work. So T in the front. So the denominator of this fraction is going to be what now?
381.
Good. So I'm interested in these 381. Interested in these 381 millennials. I'm interested in the 381 millennials, right? And again, a lot of those 381 millennials, I'm only interested in the 175 ones that were stressed. So we do 175 divided by 381. And I get 0.459. Is feeling tense or stressed out at work an age group independent? Can I answer that question based off of these two things here? Yes or no? Can I answer that question based off of those two things?
Yes.
How? What would I do?
They don't equal each other. So they're not.
Try that again. Let's go back to this real quick. Definition says that it has to be equal to probability of A given B has to be equal to probability of A, right? That's the true definition of it. Over here, we had to show that probability of F given S was equal to the probability of F, or we had to show the probability of S given F was equal to the probability of S. Are we showing that right here? Is that what this is showing between A and B?
Yeah.
Is that what this is showing between A and B? Probability of A given T is equal to what? It's not showing that. Probability of A given T is just a conditional probability.
Yeah.
If they're independent though, what should be true? If they're independent, the probability of A given T should be equal to what?
Probability of T.
Probability of
Probability
A.
of A in the front with probability of A. Or I can show what? The probability of T given A should be equal to what?
Probably.
Probability of T.
Probability of T, good. So this is just part of the independence process. This is the conditional part. You've already proven this part. We need to go show probability A now, or probability T. Well, probability of A is a very simple probability to calculate. It's just going to be all of the millennials divided by the total sample. So the probability of A is literally going to be 381 divided by 954. So 381 divided by 954, I get 0.399. So this is 0.399. I've already calculated this up here. That was equal to 0.489. Are these two values equal? Yes or no?
No.
No. So what does that tell you? They are
Dependent.
they are dependent this time. And again, if I show it over here, I've already calculated this value as 0.459. I need to calculate the probability of T. Well, the probability of filling tents, or yes, T, is 358 out of 954. That's equal to 0.403. Are they equal to each other?
No.
No, we wouldn't expect them to be equal to each other, because if it's not independent here, it won't be independent here as well. So again, this is no. That shows that they are not independent. So again, independence works. It works on its principle saying that if two things are truly independent, then it really doesn't matter if this one event occurs ahead of it, because it won't have an effect on the other event occurring. That's what you're saying. For instance, when they look at, a lot of times you look at independence when you talk about jobs and gender. If your gender really doesn't matter, then if you look at a supervisor role, the percentage of males should be pretty much consistent with the percentage of females that are in the total sample. So if you have, for instance, 100 people in your sample where 70% are males and 30% are females, if gender really didn't matter, or let me flip that around, let's go 70% females because it's Women's History Month, and 30% males, then you shouldn't have, if you looked at the percentage of supervisors, for instance, then you should have 7 females that are supervisors and 3 males that are supervisors. It shouldn't be flipped where you have 7 males that are supervisors and 3 females that are supervisors, because you're basing it off of the percentages of the entire sample. All right. And so that's what independence does. Independence bases off the percentage of the entire sample, not just the actual categories. All right. So independence is a strong concept in probability. It's one of the ones that we rely on a lot, and it's what we use the conditional for. The other thing we're going to use the conditional for is this thing that we call Bayes' theorem. And Bayes' theorem is another form of conditional probability, which says that if two events are, if we know some form of information, if we know something, right? If you already know information already, just like you do in a conditional, then what are the chances that if this event occurs, this other event is going to also occur? So it's just a conditional. And I'll give you an example of what this means. We use it a lot in medicine, or use it a lot with health. And what it says is that if, for instance, let's say that there is this rare disease in the population, and I mean extremely rare. When I say rare, I mean like 1 in 1,000 people get this particular disease. You go to a doctor and he tells you have this disease. It's a disease where 0.001% of the population, or 0.001 of the population actually gets this particular disease, right? So it being so rare, and the doctor tells you have the disease, what should be the first thing you do once the doctor tells you have the disease? Anybody know?
Get a second opinion.
Good job, whoever said that. Great job. You get a second opinion. And you get a second opinion because if this disease is that rare, 1 in 1,000 people get it, the chances that you actually got it are extremely, extremely low. And generally what happens is we find out that it's the actual test they're using. It's the test they're using, which is producing what we call a false positive, right? And so Bayes' theorem looks at stuff like that. So here's an example. You have a cough and a fever. There's a chance that you have caught COVID-19. You don't know what the chance is. You don't want to take chances, so you seek advice from your doctor. The probability of catching COVID is 1%. For a person who tests positive, there's a 90% chance this person actually has the disease. However, this test also produces a positive result 10% of the time for those who do not have the disease. You have tested positive for COVID. What is the probability you actually have the disease? Right? So let's start here. What has to be true? What has to be true, first off? Either you
That you
have the
got
disease or you got to test. So either you have the disease or you don't have the disease. Before I continue, either you have the disease or you don't have the disease. What are those two events called? Are those two events mutually exclusive or are they independent?
mutually.
Exclusive.
They're mutually exclusive. If one occurs, the other one cannot occur. I'm going to make a tree. I like trees for these type of problems. And I'm going to convert that tree when I'm done to a table. So either you have the disease or you don't have the disease. The probability of actually having the disease is what?
1%.
So I'll put on this branch 0.01. That's 1%, which means that the probability you don't have the disease is what?
0.99.
0.99. Does everybody understand why? If you have it
Yes.
at 1%, then there's 99% chance you don't have it. Now, here's what's going to happen though. You're going to take a test. That test can come back either positive or negative. If you have the disease, it can come back positive or negative. If you don't have the disease, it can also come back positive or negative. The percentage of people who actually test positive that have the disease is what?
90.
90%. So on this branch, I'll put a 0.9. Which means the people who have the disease and don't test positive is going to be what then?
0.1.
0.1, 10%. 10% of people don't test positive. What are these people called, by the way, that have the disease and don't test positive? Medically, what are they called?
False
Say that
negative.
they are false negatives. Good, they get a false negative. But then there's also a 10% of the time for those who do not have the disease, they also get a positive result. So these people also get a positive result 10% of the time, where these people get a negative result 90% of the time. What are the people that don't have the disease but get a positive result called? What are they called?
False positive.
They're called false positives. In this particular case, which one is the worst? Which one is the worst error? The false negative or the false positive?
False negative.
Negative.
False negative. Good. The false negative is the worst error here because people are walking around and don't know they have the disease. Here, if you get a false positive, they just test you again. Right? So now, if I want to calculate the actual probabilities, I just multiply the branches. That's all I have to do is multiply branches. That's how this works. So I'm going to multiply 0.01 times 0.90. So in this first branch, this is 0.009. 0.01 times 0.10. This is 0.001. Again, if I add these two branches up, what do they add up to? That 1% sitting out here. Now, the other branch, 0.99 times 0.10. 0.099, and then 0.99 times 0.90, 0.891. Again, add those up, you get your 99% on the outside, right? If I add up all of these, what do they add up to? What do they add up to?
10%.
Try it again.
100%.
Add up all 100%. Add up all of them, they add up to 100%. And so now I'm going to convert this to a table. Here's my table I'm going to convert. Either you have the disease or you don't have the disease. Either you test positive or you test negative. What percent of people have the disease and test? So in this first box right here, right? First box, they have the disease and they test positive. What's that going to be? 0.009. This next box, they have the disease and they test negative. What's that going to be? 0.001. If I add up all of these values right here, if I add this entire row up, this tells me the percentage of people who have the disease, which is 0.01. These people down here have they do not have the disease, but they test positive, 0.099. These people do not have the disease and they test negative. Do not have the disease and they test negative, 0.891. If I go across that row, this equals 0.99. Now, here's what I'm getting. Here's the new values I'm going to get from this table that I can see now. So this was already known. These are the values I'm getting now. I can actually calculate the number of positives, the percentage of positives that I have in the sample. So your percentage of positives are 0.009 plus 0.099. 10.8% of the people test positive for this particular disease. That's what this is saying. And then 0.001 plus 0.891. 89.2% of the people test negative for it. These all add up to 1.00, like this. So what we've done so far is we've just created the actual scenario. We've made a tree and a table for it. I have not answered the question yet. The question is this, though. You have tested positive for COVID-19. What percentage of people test positive for this disease?
0.108, 10.8.
0.108 test positive. So 10.8% of the people test positive for the disease. The question is, what is the probability that you actually have the disease? This is a conditional probability. This is a conditional probability. In order to fit into the sample, what has to happen first? You have to have did what?
Had a positive test.
Had a positive test, good. So the probability of, you have to have a positive test to get into the sample. That's the back. You're restricting it to the positive people. And we said that that is 0.108. Out of those people, who am I interested in? The ones that actually did what? What's the probability you actually
Have it.
have the disease? So we're looking at the people that have D, the disease, D.
So 0.01.
So at the top, what do we put at the top first? Who goes at the top? I'm interested in all these positive people to begin with, right? But after I find those positive people, what people I'm interested in now?
The total.
The ones that have the what?
I have it 0.01.
This right here at 0.099. 0.09. 0.009 are the ones that I'm actually interested in. Because these people did what? What did these people do? These people tested positive and they actually had the disease. That's what this is saying, right? And really, you can look at it as out of the 11 people that tested positive in the sample, by the way, and 11 out of 1,000 people, by the way, tested positive. So you had 11 out of 1,000 people test positive. Only one of them out of those 11 actually had the disease, right? So calculating that then, divided by 0.108. If you test positive for the disease, there is only an 8% chance. There's only an 8% chance that you actually have the disease, which is why things like this you go get second opinions on. It's only an 8% chance you have the disease. Typically what that means is that there's probably a high false positive rate. But we need high false positive rates to make sure we get the test right and we don't miss them when we have to. All right. It's called Bayes' theorem. The more you do, the better you'll get at it, the more comfortable you'll get. The Bayes' theorem always starts off by giving you a condition. And then once you have that condition, once you're able to restrict your sample to something, right? You're going to look at who's in the sample now. I'm gonna calculate from there. So let's do one more example like that. And I'll give you a few minutes to actually try this one yourselves, all right? So go ahead and try to make a tree and try to create the table. And I'll jump into this. So it says the test for a disease gives a correct positive result with a probability of 0.95, 95%. When the disease is present, it gives an incorrect positive result, a false positive with a probability of 15% when the disease is not present. If 5% of the population has the disease and gene test positive to the test, gene test positive for the test, what is the probability that gene really has the disease? Let's write this out. So again, I always start with a tree. So either you have the disease or you don't have the disease. 5% of the population actually has a disease, which means what percentage doesn't have the disease?
95.
95%. So 95% of the people don't have the disease. And of the people who have the disease, you're going to either test positive or you would test negative. Of the people who don't have the disease, you either test positive or negative, right? 95% of the people who have the disease test positive, which means that 5% of the people who have the disease don't test positive. They get the false negatives. And the next part says that of the people who take this test, 15% of those get an incorrect result that says they have it when they don't. So that's my false negative. So 15% of these people test positive, which means what percentage doesn't test positive?
85.
85% doesn't test positive. Good. So now we need to calculate these. And these are just our joint probabilities, by the way. So you have 0.05 times 0.95, 0.0475, 0.05 times 0.05, 0.0025. And again, if you add 0.025 plus 0.0475, I get 0.05 again. So those are adding up right. You can always check yourself, by the way, by doing that. 0.95 times 0.15 on the next branch, 0.1425, 0.95 times 0.85, 0.8075. All those values add up to 1. If I want to create the table, I can do that now. So you have the disease or you don't have the disease. You're going to either you test positive or you test negative. The disease and positive. The disease and negative, or yeah, the disease and negative. Total percentage. No disease and positive. No disease and negative. Total percentage. And now we can get the number of positive tests, the percentage of positive tests, and the percentage of negative tests. 0.0425 plus 0.1425. So 18.5% of the people who take this test are going to test positive for it. 0.025 plus
I think that was
0.087.
supposed to be 0.19.
Oh man, thanks. That is supposed to be 0.19. I must have added that. Oh yeah, I did. It's 0.475, huh? Good catch. Yeah, 0.19, you're right. Thank you. There we go. That means that the other one should be 0.81, right?
Yes.
8075. Yeah, 0.81, total of 1.00. So I want to know, what is the probability? Gene tests positive. So Gene has tested positive. Given that probability, what's the probability that Gene really has a disease? So what do we put at the bottom here? What goes at the bottom of the fraction?
0.19.
0.9. The 19% of people who have tested positive. What goes at the top of the fraction?
0.0475.
Good job. So we do that. 0.0475 divided by 0.19. There is a 25% chance that Gene has this disease. So that is what we call Bayes' theorem. Are there any questions on Bayes' theorem?
One question. So
I'm
the
listening.
portion where it says if 5% of population has the disease, where did we use that
Right.
5%? Nowhere?
Up here in the front.
Yeah, okay.
These are the people. These are the people who have the disease. If 5% have the disease, 95% don't have the disease. Your
Okay.
tree always starts off with the tree always starts off with the disjoint events. All right. And generally speaking, you have two disjoint events, but like this event can occur for both these positive and negatives, just like this event can occur for both the positive and negatives. They're technically disjoint events, by the way, because they're sitting here in the table. You can't be positive and negative at the same time you take the test. We start off, we have to start the tree somewhere. We generally start with the disease part here first. Any other questions on it? All right. So any other questions on conditional probability? Then, because this is all conditional probability. Any other questions on how to set those conditions up? Then remember in the conditional probability, the bottom of the fraction is the letter on the left, on the right. I'm sorry, and the other one we start with the restriction first. Then we go back to the top by looking at both of them together. All right, cool. So